Section 1.1 this year for physics. And what we're looking at here is a quick review of our physics toolkit. Same tools that we use in chemistry, a lot of them are, but they're very useful for us still in physics and they're useful everywhere in the science. But the first thing we want to start off with today is exactly what is physics. Well, physics is quite a bit different than chemistry, where chemistry was that study of the submicroscopic world, atoms and molecules and what's going on at that level. As we look at physics, we're actually looking at the study of the physical world around us. We're looking at that macroscopic world. We're looking at the world that we can see, we can touch, we can experience. So that's most of what we're looking at. We're looking at what effects are happening here, what's making things happen, the world that we can see. But physics does also deal with that submicroscopic world and rules what's happening with atoms as well. That's a big part of it also, but that's not the part we're getting into. We're pretty much going to be looking at our macroscopic world, the world we can see, experience, and be able to explain behavior and predict future behavior here in this world around us. Now, one thing that you're going to find out with physics this year too is that there is quite a bit of math in physics. Don't be scared about that. Okay. I know you're going, oh no, math, I hate math. But math is actually really important for us. Math is a great tool for us as physicists. In fact, without math, physics would be a lot different, but it wouldn't be quite the tool and the predicting tool that it actually is. In fact, we can actually think about physics as being applying the math you've been learning all along. You won't have to do anything too complicated if you're in trig right now or have had trig. It's a basic sine, cosine, tangent, sine law, cosine law stuff. That's all we're really looking at, Pythagorean theorem kind of things at the most level. Most things are still your algebraic work and getting that kind of finished back up. Well, as we keep jumping in, one of the first tools that we want to take a really quick look at is the SI system. Refresh our memories about the SI system, otherwise known as the metric system. And basically, the first thing we see is that the metric system or SI system consists of 7 fundamental or basic quantities. 7 quantities that are the most simple base units of things that we can measure. So the basis of all other measurements is another way to think about that. And here are those 7 fundamental units: length, mass, time, temperature, the amount of a substance, how much substance you have, electric current, and luminous intensity. And you can see what the units are for each of those, what the base units are and the symbols for them. Every other unit, every other measurement that we can make in the natural world is then something that comes from these 7 fundamental quantities, and therefore what we call a derived unit. It's some mathematical combination of 2 or more other units. We use both fundamental and derived units, and they both work the same within the metric system. We just want to make sure we know what the difference between them are. Okay, so within the metric system, or the SI system, I guess I should say, we're basing a system on a number 10. It's basically a number of prefixes that move your decimal point one place at a time. And those prefixes that we're going to use this year in physics are all listed here: femto, pico, nano, micro, milli, centi, deci, kilo, mega, giga, and tera. Even though we won't see tera very often, we'll basically go pico to giga. And this is actually upside down. When I usually write this, I usually write the bigger numbers on top, so tera on top, and then femto would be the very bottom, the smallest value. And as you're writing these down, maybe you want to do that as well. Now, either way, it won't really matter a whole lot. But actually, it probably will if you do it this way. No, it won't matter. But what we're going to do for conversions, just to remember how to make conversions from one metric unit to another metric unit, to make those conversions, use the exponent values in your scientific notation. Take the number that you start with. Let's say I'm going from millimeters to kilometers. I have how many millimeters I have. I take the exponent on milli, -3. I subtract from that value the exponent of the prefix that I'm going to, in this case kilo, with 3. So -3 minus 3 is -6. That -6 says move your decimal point in your value 6 places. The negative means to the left. If it was positive, be to the right. Vice versa. If I had 300 kilometers, how many millimeters was it? Kilo is 3. Minus milli, which is -3, that's +6. Move your decimal point 6 places to the to the right. So 300 becomes 300 with 6 more zeros, 300 million, or 3 times 10 to the 8th. Pretty simple for conversions, if you remember that. We'll work on some of those in class. Dimensional analysis. Now you may remember a little bit about dimensional analysis from chemistry and the fact that you didn't really maybe like it a whole lot because the biggest reason is it takes too much time to write all my units down all the time and then check them over. Well, one thing we're going to find out in chemistry is that, or in physics, much more so than in chemistry, it's much more important to pay attention to your units. Your units are of utmost importance now. So what all dimensional analysis is, it's letting us treat units like an algebraic quantity, like any other number or any other variable, and cancel them and multiply them, divide them, and so on and so forth. And it lets us check our work and set up conversions. And just a couple little cartoons for you. And we'll do a couple of dimensional analysis examples in class, and we'll really work on using those examples, because what we find out in physics is that the units will tell us if not only are we doing things right, but it lets us simplify our units to tell us what new units that we're talking about. There's a ton of things that we will do with those. Now, significant figures, the next thing we're just going to touch on again very briefly. Here in this discussion, we'll talk about them a little bit more in class, but you might remember them as your worst nightmare from chemistry for a while. It probably will seem quite a bit easier this time around. But basically what we're looking at sig fig is a sig fig, or a significant digit, is all the valid or measured digits in a measurement. Okay, so it's everything we've measured and we know for sure, plus that one guess number or that uncertain number in a value. And the uncertain number is always going to be the last significant digit. So it's really important to understand what significant digits are and be able to tell what your guess value is going to be, because it might be a 0, it might not be a 0. And you need to know what that is, because it's telling us how good our equipment was that we're making our measurements with. Now remember that sig figs are not always necessarily every value in the measurement. And here are 5 rules, which I'm just going to leave up here, and you can pause at any point in time and write these down again if you want to. I'm not going to restate them all, but we will work with these rules in class again in a few examples and try and get the hang of it again, because we want to be very good at using sig figs, and be able to look at measurements and say, hey, how good is this measurement? How poor is this measurement? How good is our measuring device? How much can we trust this value? And just an example here on the right side of this little cartoon, sig figs, or significant figures, a cup of coffee is approximately 200 milliliters. If you add 1 drop of water to it, does that mean you now have exactly 200.05 milliliters, or still approximately 200 milliliters? Okay, I'll let you decide which one it is, or you think it is, and we can talk about that in class. And then there's Tom and Becky there with his significant digit. I still will use some jokes this year. Okay, scientific method. As we take a look at the scientific method, we're basically just looking at the accepted process for solving problems in science. And a couple of terms that we need to look at again and just think about are hypothesis, theory, and law. Remember that hypothesis we always have learned from elementary school, that's an educated guess. A much better definition for us in terms of physics will be that prediction of behavior. Okay, that's a great way to think about it. It's a prediction for what's going to happen, what we think is going to happen. A theory, a lot of times we try and think about something that's not quite proven yet, but remember, that's not correct. A theory is an explanation as to why something happens. So a theory is telling us, why did this occur? A law, we like to think about, or kind of think from our elementary days, as being something that's been proven enough times. Remember, that's not what it is. It's actual behavior that we see occurring in nature. Or in other words, it's the what happens. And remember, there's a difference between being what happens and why it happens. What happens is the law. Why it happens is the theory. Okay, and that's it for section 1 today. We'll talk more in class as well about how to do calculations using sig figs and measurements. And we'll go on from other sections real quickly after that with measurements and graphing, and that'll be into chapter 1, and then we'll start getting into some of our more interesting information. See you in class.